This is a walkthrough of an A-level further mathematics, further statistics 1 specimen paper. Question number 1. In a randomly selected week, a camera recorded the number of speeding drivers on a particular stretch of motorway. So we've got the different days of the week, Sunday through to Saturday, and the frequency at which the number of speeding drivers were caught on a particular day. Jeremy believes drivers are equally likely to be recorded speeding on any day of the week. Carrying out a hypothesis test at the 5% level of significance to see if the data supports Jeremy's belief. You should state your hypothesis, the degrees of freedom, and the critical value used for this test. So we need to start with H0 and H1, and the key to working out what we're going to write for H0 and H1 is what Jeremy believes, that they're equally likely to be recorded speeding on any day of the week. So in a moment, when we work out the expected frequencies using the fact that this is a uniform discrete distribution, then H0 is going to be that it fits that distribution. So that would mean that H0 is drivers are equally likely to be recorded speeding on any day of the week. We're literally just copying out Jeremy's belief here. And H1, drivers are not equally likely to be recorded speeding on any day of the week. So we now need to start by working out our test statistic, which is x squared, goodness of fit. And I'm going to use the formula, the sum of the observed squared over the expected, and then once I've worked that out, subtract n. I find that quicker to use than the other formula, which is the sum of the observed minus the expected squared over the expected. I just find that longer to do, so we'll just use this quicker form here. Now if we're going to use this formula, or even the other form, we need to work out what the expected frequencies are. Now, as I said before, this is a discrete uniform distribution, so we should expect the same number of drivers recorded speeding on any day of the week. So that's going to be the total number of drivers that were recorded speeding, so the total of all of these, divided by the number of days, which is 7. So I'm going to do 35 plus 30 plus 28 plus 24 plus 40 plus 51 plus 37, and I want to divide that all by 7. That gives you a total of 245. Divide that by 7 and we have 35. So 35 is my expected frequency for every day of the week. So I could actually maybe add another row down here, the expected frequency, don't need to, but they're all going to be 35s. So now I can do my calculation for my test statistic here. So I want the sum of all the observed squared over the expected. Now it's going to be like 35 squared over 35 plus 30 squared over 35 plus 28 squared over 35 and so on. They're all over 35, so I don't need to write these as separate fractions. I can write them all as one fraction. So 35 squared plus 30 squared plus 28 squared plus 24 squared plus, let's get this 7 and this calculation out of the way, I don't need that anymore, and then plus 40 squared plus 51 squared plus 37 squared, all over the expected frequency, which is 35, because they've all got the same expected frequency. And then I subtract from that the number of observations, and that's this 245. And that will give us 1811 over 7, so for this bit in brackets, minus 245, that's 96 over 7, which gives us 13.7142 and so on. Okay, so there's my test statistic. I now need my critical value, chi-squared, and to find that I need the degrees of freedom. Always check the expected values. None of these are less than 5, so I don't need to combine cells. So I've got 1, 2, 3, 4, 5, 6, 7 cells. So degrees of freedom is going to be 7 minus 1 is equal to 6. Always write this calculation out even if it's obvious. So that means I'll be looking up from the formula book, 6 degrees of freedom, 5% level of significance. You can also use your calculator to work it out, but by the time you've done your calculator, it's probably going to be easier to just look it up in a table, and that gives me a critical value of 12.592. Now I compare my test statistic with the critical value. It's greater than the critical value. The spread is too much than this sort of limit value here. So that means that I'm going to reject H0, and then we need to finish with a conclusion in context. So I would write something like, therefore there is insufficient evidence to support Jeremy's belief. Now we don't need to state his belief again, it's already written in the question. His belief is that drivers are equally likely to be recorded. We've shown that the evidence shows that they're not equally likely to be recorded speeding on any day of the week. We don't need to say that whole sentence again. His belief is stated here. Is there evidence to support his belief or not support his belief? That's fine for a conclusion because his belief is stated in the question. Question 2. The discrete random variable y has probability distribution given by, and we have y here where it can take values of a, 2 and 7, and the probability of y is 1/2, 3/10 and 1/5, where a is a constant here. Given that the variance of y is 2.8 and the mean of y, e of y, is less than 0, in part A we need to find the value of a. So let's start by working out e of y from the table, the mean of y. So that's going to be 1/2 times by a plus 2 times by 3/10 plus 7 times 1/5. So that simplifies to e of y is equal to 1/2 a plus 2. Since we have the variance of y, we'll need e of y squared. So that will be a squared times 1/2 plus 2 squared times by 3/10 plus 7 squared times by 1/5. So that simplifies to e of y squared is equal to 1/2 a squared plus 11. So we can now put these together for var y. So remember, let's write it over here, that the variance is equal to e of y squared minus e of y, the mean, squared. Now the variance is 28, so I have 28 is equal to e of y squared, so that's 1/2 a squared plus 11, minus the mean, all squared, so we'll put that in brackets, so 1/2 a plus 2 all squared. So expanding out the brackets gives me negative 1/4 a squared minus 2a minus 4. So let's put this all together so quadratic. So 1/2 a squared minus 1/4 a squared is 1/4 a squared. There's just a minus 2a on its own, and then 11 minus 4, so that's going to give me plus 7, and then minus the 28 will give us negative 21. Solving this on my calculator gives me two values for a. Either a is equal to 14 or a is equal to negative 6. Now, which one of these do we choose? Well, we were told here that the mean of y is less than 0. So if the mean of y is less than 0, which we've got here, 1/2 a plus 2 is less than 0. If a were at 14, I would get 7 plus 2, 9, that's not less than 0. If a is negative 6, I would get minus 3 plus 2, which is less than 0. So therefore, a has to equal negative 6. Part B, find the mean of e of 1 over 3 minus y. So what I'm going to do is just create a little new table here which I can use to work out the mean of 1 over 3 minus y. Now I know the value of a is -6, so I'll put this in here. So basically I'm just going to do 1 over 3 minus each of these values. So if I start with the first one, it'll be 1 over 3 minus -6, so that'll be 1 over 9. Let's put that in. Then the next one, it will be 1 over 3 minus 2. 3 minus 2 is 1, so 1 over 1, that's just 1. And then the last one, 1 over 3 minus 7, so that's -4. 1 over -4, so that's -1/4. So then that mean is going to be 1/9 times a half, plus 1 times 3 over 10, plus -1/4 times by a fifth, and that gives me exactly 11 over 36 for the mean of 1 over 3 minus y. Question 3. Tim and Sue are each typing a manuscript and they make errors at random. On average, Tim makes 0.45 errors per page, so let's just underline that. 0.45 errors per page, and Sue makes 0.2 errors per page, so it looks like Sue's slightly better than Tim. A random sample of n pages of Tim's typing is taken. The probability that these n pages contain no errors is less than 0.05. Part A, find the smallest possible value of n. So this part here, this is optional. I'll have my random variable t for Tim, and this is going to be the number of errors that Tim makes in n pages. So t is going to be a Poisson distribution where the number of errors that Tim makes is going to be 0.45 times the number of pages n. So remember, we can scale up and scale down this 0.45 depending on the number of pages. Here it's n pages, so 0.45n. And we've been told in the question that the probability that he makes no errors, the probability that t is equal to 0, is less than 0.05. So we need to use the formula to work out like Poisson PD, and it's this formula here, e to the negative lambda times by lambda x over x factorial, and here lambda we're going to replace with 0.45n, and we're going to solve for n, and x is going to be equal to 0 because we're working out probability x is equal to 0. So if we plug those in, we'll get e to the negative lambda, so e to the negative 0.45n, times by lambda, so that's 0.45n, to the power x, which is 0, all over 0 factorial, and that needs to be less than 0.05. Now anything to the power 0 is 1, so we can scrub that out, and 0 factorial is 1, so we're just left with e to the negative 0.45n is less than 0.05. Next step would be to do the natural log of both sides, as we want to get rid of e. So natural log e to the negative 0.45n is less than natural log 0.05. Now the e and the log will cancel out, just leaving us with negative 0.45n, I missed the n out there, negative 0.45n is less than natural log 0.05, and then I'll divide both sides by negative 0.45, which means reversing the inequality sign, so I've got natural log 0.05 divided by negative 0.45. Let's see what that gives us. N has got to be greater than, and n is going to be greater than 6.65718, and so on. Since n has to be an integer, the smallest possible it can be is n is equal to 7, because it's got to be greater than that 6.6 number. Okay. Moving on, the random variable x represents the total number of errors. So we're looking at the total number of errors in a random sample of 5 pages. So 5 pages of Tim's typing and 5 pages of Sue's typing. Part B, find a probability that x equals 2, stating a necessary assumption. So this is when we can add together the number of errors that they make, or the probability of the number of errors they make over 5 pages. So for Tim it's 0.45 times by 5, scaled up to 5 because it's 5 pages, and so we're going to put plus 5 pages of Sue's writing, so she makes errors at a rate of 0.2, so it's going to be 0.2 times 5. So that will give us x with a Poisson 13 over 4, or 3.25. Let's call it 3.25. And we want to work out the probability that x is equal to 2. So we can just use our calculators and Poisson PD. Or you could use the formula, but I guess the calculator is going to be quicker. And we get 0.204776 and so on. I'll give an answer to 3 significant figures, so 0.205, and I'll just put here that I've rounded to 3 significant figures. Now we also need to state a necessary assumption that we've made. What we're assuming is that Tim and Sue make errors independently. Moving on, random samples each containing or consisting of 5 pages of Tim's typing and 5 pages of Sue's typing are selected. Part C, find a probability that in 10 of these samples there are at least 2 with no errors. So this is where we combine binomial with Poisson. It's binomial because we've got a sample of 10 and we want to find at least 2, and then the Poisson bit is with no errors. So let's start with the Poisson bit. What's the probability that there are going to be no errors? So it's the same as before because we've got 5 pages of Tim's, 5 pages of Sue. We worked out the Poisson for that, that's 3.25. And then working out the probability that x is equal 0, Poisson PD, and we get 0.0387742, and it carries on like this. So this is my probability of success that's going to go into my binomial. Let's just use the next letter in the alphabet. So we've got x, let's go for y. So y is going to be binomially distributed. We have a sample size of 10, and the probability that they're going to contain no errors is this value that we've just worked out. I'm going to try and use the exact value if possible, so 0.03877 ... and I want to work out the probability that there are at least 2 with no errors. So at least 2 is going to be not x but y, 2 or more. That's equal to 1 minus the probability that we have less than 1. That's like the probability of 0 and 1 added together. So I go to binomial CD, and then I actually pressed the answer button when it was asking for the probability. N was 10 and x as 1, so it's going to be 1 minus, and I get 0.9449 and so on, and that gives me 0.055003 and so on. Remember, 3 significant figures, so this will be 0.550. So 0.0550, and that's again to 3 significant figures. So you often get these questions where you've got a Poisson, that's your probability of success, and then that's part of a binomial question. So my success, which was here, goes into here in the binomial. Question number 4. The discrete random variable x is binomially distributed with n and p, and it has a probability generating function given by 0.4 plus 0.6t all squared. Part A, write down the value of n and the value of p. Now, any question that says write down means that there's going to be no working involved, and we should be able to write down the answers. Now, from the formula book, it just tells us that if x is a binomial distribution with n and p, this is how its probability generating function is given: 1 minus p plus pt to the power n. Now all we need to do is to match those values up, so I can see n is 2. It matches up, doesn't it? And so I can write down n is equal to 2. And it doesn't need any rearranging or anything because it's in this format. I've got 0.6t here, and this bit is equal to 1 minus p. P would be 0.6. So it all matches up, and so I can just write down p is equal to 0.6. Sometimes you might need to rearrange this a bit to get it into this format, but just to show you, that 1 minus p there is equal to 0.4. P, that bit there, is equal to 0.6, so it all matches. Using the probability generating function, find, and the first part of part B is the probability that x is equal to 1. Now to do that, we need to find the coefficient of the t to the power 1 term, and to do that we need to expand the brackets. So we've got 0.4 plus 0.6t all squared. So if you expand the brackets, you get 0.4 times by 0.4, which is 0.16, plus, then we'll get 0.4 times by 0.6t, that's 0.24t, that's going to happen twice, so that'll be 0.48t. Now I can stop here because this coefficient here is the probability of of 1, sorry. But I want to carry on and expand the whole thing in case I need it later on. So the next bit will be 0.6 t times by 0.6t, which is 0.36 t squared. So the coefficient of t, or you could think of it t to the power 1, that's my probability of 1. So the probability that x is equal to 1 is equal to 0.48. The second part of part B is to find e of x. Now at this point I could actually write down the probability distribution of x to find e of x. I don't really think that's what they want us to do, but it's easy enough to do because the outcomes are going to be the powers of t, which are 0, 1 and 2, and then the probabilities are going to be the coefficients, which are 0.16, 0.48 and 0.36. So if I did 0 times by 0.16 plus 1 times by 0.48 plus 2 times by 0.36, that will give me e of x, and that will give me e of x is equal to 6 over 5 or 1.2. But we're going to do it the proper way, and that is that e of x is equal to our probability generating function differentiated and then 1 substituted into that. So let's differentiate our probability generating function first. So that will give us 0.48 plus 0.72t. Now we'll put 1 into it, and then that will give us 0.48 plus 0.72 times by 1, and that gives us the same answer, 6 over 5. I think they're expecting us to use the actual probability generating function way rather than a table. Sometimes the table is just not practical to do on a question like this, so just go for using the formula. It's in the formula book anyway to find e of x. Moving on, 2 independent observations, x1 and x2, are taken from the distribution of x. The random variable y is equal to x1 plus x2. Part C, use calculus to show that e of y squared is equal to 6.72. Now the formula book tells us that if z is equal to x plus y and x plus y, or x and y independent, then the probability generating function for z is equal to the probability generating function for x times the probability generating function for y. Now we can use exactly this, and we can just replace the z with y. Okay, it's the same thing, and then we can replace the first x with x1 and the second x with x2. Okay, so we can just do this and adapt the formula to what we got. Okay, however, x1 and x2 are taken from the distribution of x, so there is no x1 and x2, they are just x. So my probability generating function for y is going to equal the probability generating function for x times itself, the probability generating function for x here. So here's the PGF for x times by itself or squared. So when we square anything, we double the power, so I can write it as power 4. Now to help us find e of y squared, it does say use calculus, so we can't use a table, we've got to use differentiation. First of all is the formula for the variance, which is where you differentiate twice, substitute one, and then you find the mean, and then you subtract the mean squared. Now the variance formula is e of x squared minus the mean squared. Now if you match these up, the bit at the end, which colour shall we use? I said blue or something. So this bit at the end, that's probably not the best way to do it, matches up with this. Okay, I'll take that off in a minute. But the bit I'm interested in is the middle bit here, or the first bit. So e of x squared matches up with this. So this is e of x squared. I want e of y squared. So I'm going to have to differentiate once and twice, substitute one in. When I add those two together, that matches up with e of y squared. So maybe I'll write that down first. So e of y squared is equal to the probability generating function for y differentiated twice, we substitute in one, plus the probability generating function for y differentiated once with one substituted in. So let's work out those bits first. So let's differentiate the probability generating function once, okay, which is this here. Now we can just use the chain rule, which is differentiate the outside. So I'll have 4 at the front, 3 here, then multiply by the inside differentiated. So I'll have 4 times by 0.6, so that'll give me 2.4 at the front. So 2.4, inside doesn't change, 0.4 plus 0.6 t cubed, all cubed. So that with 1 now substituted into it, so I'm basically working out this part here. So dg dash of y with 1, so 2.4 times by 0.4 plus 0.6 times by 1 cubed. Well, this bit in the bracket is just going to be 1, and so we just get 2.4. Let's differentiate it again. So g double dash of y with t. So we do the same thing using the chain rule. So differentiate the outside, so that's going to be 2.4 times by 3, which is 7.2, and then I multiplied it by the inside differentiated, so I need to do 7.2 times by 0.6, and that gives me 4.32. The inside doesn't change, so it's 0.4 plus 0.6 t, and then the power goes down to 2. Let's now substitute 1 into that and see what we get. So that'll be 4.32 times by 0.4 plus 0.6 times by 1, and that is going to be squared, all squared. Just like the last bit, this bit in the brackets is just going to make 1, so we're just left with 4.32. So that means that e of y squared is equal to 2.4 plus 4.32, and if we add those two together, we get 168 over 25, which is equal to 6.72. So I'll just put equal 6.72 as required. Question 5. A company claims that the proportion of visitors to its website who make a purchase is 0.03. Nina believes that the proportion of visitors to the website who make a purchase is less than 0.03 and asks the company for some data to test this. The company tells Nina for a particular day the number of visits to its website until a purchase is made. Nina assumes that visits to the website are made independently and that each visitor has the same probability of making the purchase. Part A, using a 5% level of significance, find a critical region for this test. State your hypothesis clearly. Now, any question where it talks about something happens until something happens and then we stop recording information is going to be a geometric distribution. So I'm going to use the letter x as my random variable. It's going to be a geometric distribution, and the probability that somebody who makes a purchase to the website is going to be 0.03. Since this is a hypothesis test, I want to state H0 and H1. So H0 is going to be that the probability that somebody makes a purchase is 0.03, and then H1 is going to be that the probability is less than 0.03. Now remember, with geometric, the upper and lower tail tests reverse, so even though that this is less than, with geometric this is an upper tail test. Now we need to find the critical region for this test. So since it's an upper tail test, it's a probability that x is greater than or equal to, I'll just call it x, needs to be less than the significant level. It's always going to be less than the significance level, which is 5%. And now it's about solving this for x. Now for a geometric distribution, the probability that x is greater than or equal to x is 1 minus p to the power x minus 1. So we'll just use that over here. So it's going to be 1 minus p, so that's 1 minus 0.03 to the power, and it's just going to be x minus 1, or whatever letter you use, is going to be less than 0.05. Now we're going to do the log of both sides to enable us to find x. So this bit here is going to be 0.97. So log 0.97. Now what's going to happen is that that will be to the power x minus 1, but then we can bring that power to the front. So x minus 1 is less than log, and we'll use log base 10. You can use any base actually. Log 0.05. Now we're going to divide both sides by a log of 0.97. Now anytime you divide by a log of a number which is less than 1, between 0 and 1, that will actually give you a negative number, which means you need to reverse the sign, and so we'll have log of 0.05 divided by log of 0.97. If you're not sure, just put this in your calculator to see what type of number it gives you. Rearranging, solving for x, we get x needs to be greater than 99.352, that's a 3 there. Now x needs to be a whole number, so the smallest value it can be is going to be 100. So now we're talking about critical regions. So when x, the number of observation, is greater than or equal to 100. So we'll just write that down properly. Critical region x greater than or equal to 100. Part B, find the actual level of significance for this test. So that's basically working out the probability that x is greater than or equal to 100. What's the actual value? And then we can use the formula again. So 1 minus 0.03, so that's 0.97 to the power of 100 minus 1, or to the power of 99. And we get 0.049023. So three significant figures. So 0.04903 SF. So that's the actual significant level, not far off actually from the 5% significance level that we were testing at. Part C. The 94th visitor to the website was the first person to make a purchase. 94 visitors before we get a purchase. Part C. What we need to do is test at the 5% level of significance whether or not there is evidence that the proportion of visitors who make a purchase is less than 0.03. So we're basically carrying on from what we worked out here. Critical region was 100 visitors. So we've got a 94 visitor. So 94 is not in the critical region. When something is not in the critical region, we would accept H0. So finishing with our conclusion, after we accepted H0, there is insufficient evidence that the number of visitors who make a purchase is less than 0.03. Question 6. The weights of bars of soaps are known to be normally distributed. The standard deviation of the weights is 3 grams. A label on the bars of soap states that the mean weight is 120 grams. So we've got a few things to highlight here. Normally distributed, standard deviation 3 grams, mean weight 120 grams. Giselle believes that the mean weight of the bars of soaps is greater than 120 grams. She takes a random sample of 10 bars of soap and finds the mean weight of her sample. Giselle then tests at the 5% level of significance whether there is evidence that the bars of soap weigh more than 120 grams. Part A. Write down the probability of a type 1 error. Now the probability of a type 1 error for a normal distribution is just the actual significance level, which is 5%. Remember, type 1 error is the probability that you reject H0 given that H0 is true. Well, the probability that you're going to reject H0 is the actual significance level, so that is just 5% or 0.05. Given that the true mean weight of the bars is 122 grams, Part B, show that the power of Giselle's tests is 0.68 to 2 significant figures. Now, to find the power of a test, that's equal to the probability that we reject H0 given that H0 is false. Now, we already know that H0 is false bit, that it says given that the true mean weight of the bars was 122 grams. So for this part, we'll have the mean is equal to 122. What we need to do over this side is work out the rejection region that we would have had with the original mean, that is with a mean of 120. So this is a normal distribution of the sample means with the original mean being 120, and the variance is going to be the variance of the population. Now it does say here that standard deviation was 3, so the variance would be 3 squared divided by n, the sample size, and the sample was 10 bars of soap. Now because this is upper tail, because it says evidence of the bars weigh more than 120 grams, we would have rejected H0 when the sample mean was greater than a critical value, which we're going to work out using inverse normal, when that probability is less than or equal to the significance level, which is 5%. So this we can work out using inverse normal. So this is just a diagram showing what's going on. It's an upper tail test. We want to find this value here. So this value, remember that the mean we're going to type in is 120, and then the standard deviation, that's going to be the square root of this, so it's going to be 3 over root 10. And the area that you need to type in has got to be the area from the left. So since this area here is 5%, we need to type an area of 95%, and that gives us a value of x equal to 121.5604. So the rejection region is when the sample mean is greater than 121.5604. So now we can work out the power of the test, and that is the probability we reject H0. We reject H0 when the sample mean is greater than this 121.56 number, given that the mean is actually 122. So H0 false means that the mean is equal to 122. So we can use normal CD to work this out. So the lower value will be 121.56044. You can just use the answer button. The upper value, just anything big like 99999. We'll put in a mean of 122, the same standard deviation, 3 over root 10, and that gives us 0.67843. And I can see that this is 0.68 to 2 significant figures as required. Moving on, Alex decides to carry out the same test at the 1% level of significance. Part C. Without carrying out the test, compare the power of Alex's test with the power of Gazelle's test. Give a reason for your answer. Now, if you decreased the significance level, a few things are going to happen. First thing it's going to do is it's going to decrease this area here, that's to the right, the rejection region. So if you decrease the significance level, this area here, it was 5%, now decreases to 1%. So the rejection region decreases. So actually the rejection region gets smaller. So rejection region decreases. As a result of that, you now have a lower chance of rejecting H0 because there's a smaller area for you to actually reject H0. And if you've got a smaller chance of rejecting H0 with a different mean, then overall your power is going to decrease. So what that means is that the power of Alex's test, because of this reduced rejection region, reduced power, is going to be less than the power of Gazelle's test. Joseph decides to increase the sample size and carry out the test at the 5% level of significance. Assuming that the true mean weight of the bars is 122 grams. Part D, calculate the smallest sample size that will produce a power of at least 0.9. So just like before, the power of a test is the probability to reject H0 given that H0 is false. Well, we know the H0 is false bit, the mean is actually 122. Now for the rejection region, because we are doing a test at the 5% level of significance, this area is 5%, so we want to try and work out what this value is here, this rejection value. And also we need to consider that the standard deviation is going to be 3 over the square root of the sample size, and that's just n, because we need to work out what the sample size is. So since we have an unknown here in the standard deviation, we do need to standardize this. So if we use the standard normal distribution here with an area of 5%, so either using the calculator or the percentage points table, you'll get a Z value of 1.6449. So using our standardization formula, it'll be 1.6449. Z is equal to X. So we don't know this value of X, we need to find it, minus the mean, that's 120, divided by the standard deviation, so that's going to be 3 over the square root of n. So if I rearrange this formula, I'll get the X value that I'm trying to find here is equal to 1.6449 times 3 over root n plus 120. So the power of my test is the probability that I reject H0. So X is greater than this value here that I need to calculate, given that the mean is equal to 122. And what I want is this to be greater than 0.9. So I now need to standardize again, because again I've got an unknown here. I still don't know what this standard deviation is because of this square root of n, but I do know that I want the area to be greater than 0.9, the power to be greater than 0.9. So if I standardize, I want this area here, I basically want to find out the critical value when that area is 0.9. So it's about finding out this value here. So if I use inverse normal and I put in an area of actually 10% over here, I'll get my Z value as negative 1.28, and you can get this from the tables as well, 1.6. So there's my Z value, and that's going to be equal to my X value, which is what I've got written here. So that's 1.6449 times 3 over root n plus 120 minus the mean, and that mean is 122 now, minus 122 over the standard deviation, well that's 3 over root n. So you can see now the only unknown I've got is root n, and I should be able to solve for n. Right, so we're going to do a little bit of rearranging to solve for n. So if I times both sides by 3 over root n, I'll get that negative 1.2816 times by 3 root n, and then 3 over root n, and then take this away from both sides. So then I'll have minus 1.6449 times 3 over root n is equal to negative 2. You can get rid of all the negative signs. Then I can put these two terms together. So then I'll get 2.9265 times by 3 over root n. And that's equal to 2. Dividing both sides by 2.9265, dividing by 3, finding reciprocal and squaring, I get a value of n equal to 19.269, and so on. And then just following through with my inequality sign, so I wanted a power greater than 0.9. So in other words, this value here to be greater than this standardized value, and then it's going to be the same symbol here, then we multiplied through by negative 1, it gets flipped around. So it's got to be greater than 19.269, so n would need to be 20. Okay, so now we can move on to the very last part here. So part E, state which of Gazelle's and Joseph's tests should be used, give a reason for your answer. Now, both of their tests, Gazelle's and Joseph's, both have the same size of the probability of a type 1 error, that's 5%, because they both use a 5% level of significance. So the probability of a type 1 error is not going to help us decide who we're going to choose. So we need to look at the power of the test. We normally look at these things together. But the power of Joseph's test with a sample size of 20 produced a power of at least 0.9, so we know that's the power of his test, whereas we already showed in part B that the power of Gisel's test is 0.68. So we would choose Joseph's test because it has the greater power. And part of the reason for that, I guess, well, the main reason for that is the sample size. He's got a bigger sample size. A larger sample size will normally produce a more powerful test. So out of the two, Joseph's, because the power of his test is greater than the power of Gisel's test. Question 7. A radio station is running a contest each day for 30 days. Each day it awards a prize to each of the first 12 callers who phone in and answer a question correctly. Once 12 prizes are awarded, no more calls are taken that day. It is assumed that each caller has a 3/4 chance of answering a question correctly, independently of all other calls. Part A, find a probability that there are exactly 15 calls taken on the first day. Now this is a negative binomial distribution because we have a certain number of successes, 12 of them, in a certain number of trials. In this case here it's going to be 15, and the last success occurs on the last trial, and then we stop. So I'll write my model down. Negative binomial, the number of successes is 12 prizes, and the probability of success of getting a prize is 3/4. Okay, now we just need to remember with negative binomial that the two values we have in the brackets are R and P. So R represents the number of successes, 12, P is the probability of success, and X is the number of trials. So here I've written down the formula that we can use for this. It can be worked out manually, which is what I do on my video on negative binomial. But when you're in an exam, you might want to just use the formula. You might find that a little bit more straightforward, less thinking really, just working out numbers and putting them in. So let's do that. So x minus 1, so that's going to be 14. So we've got 14c r minus 1, 11, times by p, which is 3/4, and that 3/4 is going to be to the power r, so to the power 12, times by 1 minus p, which is 1/4, to the power of x minus r, so it's going to be 15 minus 12, so to the power 3, and that'll give us 0.100159 and so on, and we want to give that to 3 significant figures, so 0.180. Right, moving on to part B. Find the probability that there are more than 13 calls taken on the first day. Now, more than 13 calls means that at most you can only have 11 successes in the first 13 calls. There are 12 callers who get prizes. We can't have all 12 getting prizes. So at most in the first 13 calls you can have 11 successes, then a 12th success can occur any time after that. Now we can solve this by using a binomial. 13 trials, at most 13 successes, and if we work out that probability we get 0.87329. Now there are other ways of doing this, and to 3 significant figures we'll get 0.873 SF. Part C. Estimate the probability that the mean number of calls taken over the 30 days is more than 15.5. So since this is a negative binomial distribution, the mean of a negative binomial is R over P. This is in the formula book. So R is 12, P is 3/4. So we've got 12 divided by 3/4, and that gives us 16. And the variance of a negative binomial is R times by 1 minus P over P squared. Now the reason we're doing all of this is because we're going to be using the central limit theorem to calculate this probability. So continuing with this calculation, r is 12, 1 minus p, so 1 minus 3/4 or 1/4, all over p squared, so 3/4 squared, and that gives 16 over 3. So here's my normal distribution, because we're taking a sample of 30 from this distribution, and we want to find what's the probability that the mean of that sample is greater than 15.5. So the mean is 16, so that's the mean of the negative binomial. The standard deviation of this, well, this is the standard deviation of the negative binomial, so the square root of 16 over 3, and then divided by the square root of the sample size, which is 30. We're taking a sample every day for 30 days, and we want to see if the mean is greater than 15.5. So it's always good practice to say why we're doing this. So by the central limit theorem, the mean of the samples is normally distributed with a mean of 16 and a variance of 16 over 3 over n, which is 30. The probability that that sample mean is greater than 15.5 is equal to, on my calculator, 0.88216. So we want to give that to 3 significant figures, so 0.882. So 3 SF for that one.